You will be analyzing your alcohol that you extracted using a technique called nuclear magnetic resonance spectroscopy. Since it is spectroscopy, it is using light. Specifically, we are looking at light out in the radio frequency range. So this is long wavelength, very low energy. In fact, similar wavelengths to what you have on an FM radio dial. The basic principle behind nuclear magnetic resonance spectroscopy is that nuclei can behave a bit like a small magnet. And so if we put it in a magnetic field like a compass needle, it will align with the field. We can push it away from alignment using radio waves, and that will push it out of equilibrium. When it returns in alignment, it will give off radio waves. It gives off energy in the form of radio waves, and we can measure that. Now, for nuclear magnetic resonance spectroscopy, or NMR, there are three things that we look at. One is chemical shift. This is a modified frequency, but it is related to the environment of the nucleus. We look at integration. This gives us some quantitative information, since the size of the peak, or specifically the peak area, is directly proportional to the number of hydrogens that we're giving that signal. And we also look at something called coupling or splitting. This gives us some information about how the various hydrogens are connected to one another. So we will address these one at a time, starting with chemical shift. The electrons around the nucleus influence the magnetic field, and they do change the frequency slightly. The frequency of the resonance for these hydrogens is dependent on the magnetic field. And so to make the NMR independent of the field strength, we normalize or adjust the frequency. And so when we report the frequency, we don't actually report a frequency in hertz. We report a modified frequency, which we call chemical shift. That way, it does not matter what the magnetic field strength was of the instrument we're using. The chemical shift will be the same for the same molecule, regardless of the magnet. That modified frequency, again, is called chemical shift, and the units are ppms, which is part per million. And we use the ppm scale in a manner similar to that which we use the frequency scale in IR. We look at a particular range. For example, if we have a peak between about 0.7 to 1.8 ppm, this correlates to plain alkyl-CH. If we have a peak between about 2 to 2.7 ppm, this is a CH on a carbon that is part of a double bond. For example, allylic CH. So we're looking specifically at a peak arising from this hydrogen, but notice that it is bonded or next to a carbon-carbon double bond. It is not part of the double bond. Down here we have vinylic. This hydrogen is directly bonded to one of the carbons of the double bond, and this has a different range. So this is next to. Likewise, we have benzylic. This is a CH next to a benzene ring, not the one attached to it. And it is true even if we're looking at a carbon-oxygen double bond as opposed to a carbon-carbon double bond. So this is a useful table to memorize. For this experiment, there are actually only 3 regions that are of interest, and really only 2 that are worth memorizing. One is the alkyl region, 0.7 to 1.8. The other is this alkoxy region, about 3 to 4.5 ppm. This is where we find a CH next to an electronegative atom such as oxygen. And since you are going to be using or analyzing alcohols, this is a region that is of importance. There is one other region that's of some interest, and that is for the OH. itself, although in this case we have a range 1.5 to 5 ppm that's too broad to be of any real use. So I will talk later when we are discussing actual spectra and looking at the interpretation. I will talk then about how to identify the peak that is coming from that OH. So here's an example of the way we use this. In this case we have a peak here, about 2.0 ppm, and the units are not shown here, but again the scale is part per million. And if we go back to our table, this is where we find the hydrogen. Of course, it's on a carbon here that is next to a double bond. And this could be a carbon-carbon or carbon-oxygen, carbon-nitrogen double bond, but CH bonded to a carbon double bonded to something. Out here in the 3.5 to range is about 3.7 ppm, but again this is the alkoxy region, so this is where we have our CH that's bonded to an electronegative atom such as oxygen. And again, all of these peaks, since we are doing hydrogen NMR, are due to the hydrogen itself. But then this correlates with our structure. Our OCH here is in fact from this methyl group, or the CH that's next to the double bond is in fact this methyl group, which is next to the carbonyl, the carbon-oxygen double bond. Okay, so we use the chemical shift to determine the type of hydrogen, what it is adjacent to or part of. The second factor I mentioned is integration. The peak size, more specifically the peak area, so it's not just the height, but if a peak is broad, you would need to take that into account as well, but the peak area is directly proportional to the number of nuclei. If you think back to IR, in that case, peak size was more proportional to the polarity of the bond. But here it is quantitative in that it is directly proportional to the number of nuclei. So if one peak has twice the area of a second peak, it means that first peak has twice as many hydrogens, or is due to twice as many hydrogens as the second peak. This is useful, and in fact we do need to consider the fact that you cannot have fractional nuclei, so these ratios must be whole numbers. So we can identify a peak as being due to one hydrogen, or two hydrogens, or three hydrogens. The peak area gives us the relative number of hydrogens. We have an example here. Now we have this trace that comes up and then across, and then we have another one here. This is sometimes referred to as an integral curve or an integral trace. You'll commonly see these on spectra. What's important is that the height of that trace is directly proportional to the area of the corresponding peak. In the old days, we would actually take a ruler and measure these and get these values. More commonly these days, you will have something like this underneath the peak, where it will have some number. For example, it's 43 millimeters in height, so this would be 43, 17, and 26. So this is the relative ratio. We have 43 to 17 to 26. This is not an absolute ratio, it is relative. To try to get this to some reasonable numbers, you would typically multiply one of these numbers, the 43, the 17, or the 26, by some scaling factor based on what you presume the peak to be representing. So if you think it's a CH3, you would multiply it by the appropriate factor to set it to 3, and you would do so. That same factor would be multiplied against all peaks. If you're dealing with a true unknown, so you have no clue what they are, what we typically do is divide each of these by the smallest. So 17 is the smallest. This gives us 1. 14 divided by 17 is 2.5. 26 divided by 17 is 1.5. Now, as I mentioned earlier, you cannot have fractional hydrogens. 1 hydrogen is reasonable. 2.5 is not. 1.5 is not. So when we see a ratio like this, typically we multiply everything by 2. So this actually represents 5 hydrogens, 2 hydrogens, and 3 hydrogens. And so we have a ratio of 5 to 2 to 3. And indeed, that is what these numbers correlate to. Here we have 5 hydrogens. If we look at the chemical shift, this is the aromatic region, so these are the hydrogens on that benzene ring. And we do, in fact, have 5 hydrogens associated with that. This is 2. That corresponds to this methylene. That is a CH2 group. And out here we have 3. And again, this corresponds to a CH3. And if we look at the chemical shift here, 2 is where we do expect to find a hydrogen bonded to a carbon next to a double bond. And again, a carbonyl double bond. So the third thing we look at is the coupling or splitting. At all the peaks we've looked at so far, we've seen a single peak. Something looks like this. We refer to that as a singlet. However, if the adjoining carbon has hydrogens, that peak will be split. So if there is in fact one adjoining or neighboring hydrogen, it will be split into a doublet. Gets split into 2 peaks. If there are 2 neighboring hydrogens, it gets split into 3 peaks, something we call a triplet. And the number of peaks is 1 more than the number of NMR active nuclei on the adjacent atom. And this only applies, of course, to what we're going to be looking at as symmetrical peaks. So this is an example of a doublet. Notice we have 2 peaks of roughly equal intensity. Hence we have this 1-to-1 ratio. The triplet is a 1-to-1 ratio, where that center peak is twice the size of these 2 outer peaks. And notice the outer peaks are of roughly equal intensity. Same thing with the quartet. We now have 4 peaks. Again, it is symmetrical. These 2 outer peaks are roughly the same intensity. 2 inner peaks are roughly the same intensity. And the outer peaks are 1/3 the size of the 2 central peaks. Those 2 center peaks are 3 times the size. And this is a sextet. And again, we have a very specific ratio, 1, 5, 10, 10, 5, 1, where the very outer peaks are 1/10 the size of the inner. And then we have 2 more middle peaks, roughly equal intensity, that are half the size of the inner ones, or 5 times the size of the outer ones. You may be noticing a pattern here if you're familiar with Pascal's triangle. We have 1 to 1, and then we can add the 1 and 1 together, we get 2. So this is our doublet intensity, 1-to-1. Triplet is a 1-to-1. Quartet, it's 1-3-3-1. If we have a pentet, then we would have 1, 3 plus 1 is 4, 3 plus 3 is 6, 4, 1. So that's the intensities for the pentet. And again, this is Pascal's triangle, but notice the peaks are symmetrical, and the spacing between the peaks is equal. If we saw a peak like this is not a triplet for 2 reasons. 1, the distance between these 2 peaks is greater than the distance between these 2. So this is not a triplet. Also, a triplet would be a 1-3-1 pattern. And here 2 of the peaks appear to be about the same size. It looks more like a 1, 2-2 pattern, which is not a triplet. But again, this tells us something then about the neighbors. Doublet means one neighbor. So that means we have a CH, and it is bonded to a carbon with one hydrogen. A triplet, again, the peak is due to a hydrogen, and then the triplet means there are two neighbors, which likely means it is bonded to a CH2. A quartet, again, we have our CH, the peak that we're actually looking at, or the hydrogen that's giving rise to that peak. And quartet means three neighbors. Most commonly, this is a CH3. Now, while I have been drawing this as though there is just one neighbor with all the hydrogens, that does not have to be the case. For example, we could also get a triplet if the hydrogens, we can also get a quartet if the hydrogens are on separate carbons. So we could have a CH2 and a CH both bonded to that carbon. And so we still have three neighbors. Here we have three that are all on the same carbon. Here we have three that are spread out between two carbons. But it's still three neighbors, and therefore it would give a quartet. And that becomes especially relevant when we consider something like a sextet with five neighbors. Again, we have our CH, but we cannot have a CH5 providing those five neighbors. You cannot exceed 4 bonds on a carbon, so most likely this is a CH3 on one side and a CH2 on the other, and that would provide 5 neighbors. But again, even something like a quartet where you could have all 3 neighbors on one carbon, they could be spread out between 2 or even 3. You could have a CH giving rise to the peak, and it is bonded to 3 CH1s, or 3 methine groups. So keep that in mind as we start looking at some examples. So this is one example using the splitting. Before, as I mentioned, all of our peaks were singlets. Here we have a peak that is split into 4. So this is a quartet. This is a singlet. And this is an example of a triplet. The quartet means 3 neighbors. Most common example is that means it's bonded to a CH3. Singlet means no neighboring hydrogens. And the triplet means 2 neighboring hydrogens. So then how do we put these pieces together? The first thing we're going to do or the next step that we use for the assembly is to look at the integrations. We measure the height of that integral trace, of that integral curve. We get a 1 to 1.5 to 1.5 ratio. Again, we can't have half hydrogens. So that means this represents 2 hydrogens, 3 hydrogens, and 3 hydrogens. In other words, this is a CH2. Remember, carbon can have 4 bonds total, so we'll write it this way. This is a CH3, and again, that means there's one more thing bonded to this carbon. Likewise, 3 hydrogens, so this is also a CH3. And again, carbon has 4 bonds, so this is bonded to one other thing. If we look at the splitting here, triplet splitting tells us that it's bonded to something with 2 neighboring hydrogens, so most likely bonded to a CH2. In fact, we have a CH2 here. So these 2 are likely bonded to each other. And anytime you make those connections, you should check that it works out both ways. We do have a quartet here. Quartet means 3 neighbors, so it is bonded to a methyl group. And so this connection makes sense. Of course, if we started at this end, quartet, 3 neighbors, well, we've got 2 methyl groups. We have this one here, and we have the peak at 2.0, both of which represent methyl groups. So what if we had initially gone here? Again, if we look at the splitting, a singlet tells us there are no neighboring hydrogens. We know this is the wrong connection. The splitting here works well, quartet to CH3, but our CH3 is a singlet, so it is not bonded to a CH2, so we know that one's wrong. But this one fits. So at this point we can start looking at chemical shift. This is around 4.0, but the range between 3 to 4.5 in our table means that this is bonded to an electronegative atom such as oxygen. This is the alkoxy region. At 2.0, this is the region where we find CH that's bonded to a carbon that is part of a double bond. So we have something of this sort. At about 1.2 ppm, this is alkyl, meaning this is bonded to another CH group of some sort. And so all of this makes sense then. We have these pieces. We would then put them together. We have our CH3 bonded some sort of double bond. We also have our O CH2 CH3, and most likely scenarios these are bonded to each other. And in fact we get this product that I've shown here, the ethyl acetate. And the peak at 1.5, this methyl group is in fact this one. This CH3 is this one, and our CH2 is that one right there. What we don't know from NMR is what the nature of the X is, but that's given here that it is indeed an oxygen. But from the NMR, you'll notice that we can get nearly an entire structure. So NMR is more complicated than something like IR in that we have to consider not just the chemical shift or the frequency, we also need to consider the integration and the splitting, but that extra information also gives us a lot more information to put together and is a much more powerful technique in that we can often get a specific structure. IR, for this compound, we would have basically that we have a bunch of CH, and from the carbonyl peak we would know we have a ketone or ester of some sort, but that's it. We would not know which ester. From the NMR, we know specifically that it is ethyl acetate. So this is an example similar to what you will be seeing for the spectra for your product. Again, notice that we have underneath, we have our integrations. Don't confuse these with the chemical shift. These are integrations. This is the chemical shift, which is represented by the Greek symbol delta, and the units are ppm. But it is a scale underneath, the continuous one, that shows chemical shift, and it's the little bracketed items that give the integration. And so with the integration, remember, now we have a total unknown. We don't know what any of these values should be. So to normalize it, the approach is to divide each of these by the smallest. 1.7 divided by itself, of course, is 1. 1.8 divided by 1.7 is going to be slightly greater than 1, but it's close enough. We can round that to 1. And 10.2 divided by 1.7 is going to be equal to 6. So at this point, we have a hydrogen ratio. It is 1 to 1 to 6. And we also know that we have a product that has 8 total hydrogens. Again, this is 1 hydrogen, and 6 hydrogens. Now, you are being told that this is an alcohol. Of course, if you had a total unknown, you might run an infrared spectrum first and find a strong absorption around 3400, and use that to recognize the fact that you have an alcohol, which means one of these peaks is an OH. So how do we identify the OH? For all of these, it's a monoalcohol. That means there is only one OH, which means the integration will be 1. So we have to look for a peak that integrates to 1. We have 2 of them. A second thing that we typically find with OH, that OH peaks are usually singlets, and often a broad peak, although you will see examples where it can be somewhat sharp. But in this case, we do have a peak that is broad. We don't have any clear splitting for the peak, and it does integrate to 1, so this is our OH peak. So what about the other 2? If we look at the chemical shift, this is around 4.0. Again, remember, this is the alkoxy region, so that means this is an OCH. Integration is 1, so this is CH1. And of course, carbon can form 2 other bonds. Out here, we have a peak, about 1.2 ppm. So this is the typical alkyl region, 6 hydrogens. We're not likely to have a CH6 since carbon cannot form 6 bonds. So this is almost certainly going to be 2 methyl groups, 2 CH3 groups. So at this point we have this information based on chemical shift, the alkoxy. The broad peak at 1.6 is our hydroxy, and the tall doublet that integrates to 6 would be 2 methyl groups. And so we'll draw out those pieces in this format. And then the next step is, how do we put the pieces together? And for that, we use our splitting. And so if we look at this, we definitely have 1, 2, 3, 4, 5, and it's not real clear, but if you look closely, you'll find that we actually have 2 more tiny little peaks there. So this is 7 peaks. This is a septet. So 7 peaks, that means the number of neighbors is 1 less. So this would be 6 neighboring hydrogens. Other peak that we would look at would be this one here. We have 2 peaks. So this is a doublet, meaning there is 1 neighboring hydrogen. And so all that remains then is to put the pieces together. Obviously, if this is our alcohol, that hydrogen belongs there. Septet, 6 neighbors. How do we get 6 neighbors? The most logical way is that we have 2 CH3s that this is bonded to, meaning that one of these is bonded to one of the methyls and the other bond goes to the other methyl. And of course, we always want to double check. The doublet, meaning 1 neighbor, that means these methyl groups are bonded to a CH. And so indeed, this is a CH. This carbon has only 1 hydrogen. And so that accounts for this being a doublet. And so we have this structure here. Now, when you are discussing the NMR, you will need to include an interpretation in your discussion section. In addition to explaining what the splitting and chemical shifts mean and how you're deducing your structure, you do need to make specific assignments, assign particular hydrogens to particular peaks. And so for that, we need to label our hydrogens. And so we will go through HA. So this peak is a result of hydrogen A. This one, hydrogen B. And then the 2 methyl groups, because they arise from the same peak, we give them the same label. If they are separate peaks, give them separate labels, but since both methyl groups are arising from the same doublet, we would give them the same label, and so we would label both of those C. And then when we do our discussion, we can refer to the doublet at 1.2 ppm correlating to hydrogen C. It's easier than trying to describe a particular hydrogen on a molecule, especially larger molecules. All right, so we'll look at one more example. This one's a little more complex than the last one, but again, remember that the values here, the ones that are bracketed under the peaks, represent integrations. And as denoted here, this scale represents chemical shift. So this peak here is at about 3.7 ppm. It is not at 1.47 ppm. That is an integration. And again, we are dealing with an unknown, so we will divide each of these integrals by the smallest. 1.47 divided by 0.70 tells us that this is roughly 2 hydrogens. 0.7 divided by itself is going to be 1 hydrogen. Then we have this quartet, 1.58. Again, divide by 0.7. Get a value slightly greater than 2, but it's close enough that we can simply round it 2 hydrogens, 1 hydrogen, and 4.2 divided by 0.7 is 6 hydrogens. And so we now have a hydrogen count for each of these peaks. That's shown here. Again, we could also add all these up. 2 plus 1 is 3, 2 more is 5, 6, 12, so we have a compound that has a total of 12 hydrogens. We can look again at chemical shift. One of the first things we want to do is consider which of these peaks is our OH, because again, we are dealing with an alcohol. You're being told that, but in the absence of that knowledge, you could use an infrared spectrum. So again, we're looking at a peak that has an integration of 1. We have 2 such peaks. This one was 1 hydrogen, and this one is 1 hydrogen. But the second criterion for whether or not a peak is OH is that we almost never see splitting between the OH and anything adjacent to it. Those are almost always singlets, so that takes this out of play. So the singlet here is going to be our OH. So this peak is our alcohol. And then we would use chemical shift to determine the other peaks. Again, this is out here around 3.7 ppm. This is in the alkoxy region. So this is our OCH. Specifically, because the integration is 2, it is an OCH2. And so this is OCH2. And all of the rest of the peaks are within that 0.7 to 1.8 range where we find alkyl CH. So we have these pieces here, and from the shifts we have then those particular groups. We have our alkoxy identified, we have the OH, and the others are all alkyl groups. And then the next question is, how do we put these together? Of course, we'll start with the obvious one. Since this is the alkoxy, that oxygen will be the alcohol, and so this gets bonded to it, and we get this fragment here. So now we have an OCH2. So what else is this carbon bonded to? Carbon has 4 bonds. We see 3 of them, 2 to hydrogen, 1 to oxygen. If we look at our splitting here, this is a triplet. Triplet means 2 neighbors, which means this is bonded to a CH2. If we look at the other pieces, we have a CH1, we have a CH2, so this is a possibility. CH3 and CH3. So the only thing this can be bonded to is that methylene. And so now we have this fragment. Of course, we always want to double check our work. So here, this is the CH2 we just added. This is a quartet. Quartet means that there are 3 neighboring hydrogens. So if we look at what we actually have, we have 2 neighboring hydrogens. It's supposed to have 3, which would mean it's bonded to 1 more. So we would expect to have a CH1 on this side. Question then is, do we have a CH1? And yes, we do. So this could be bonded to that CH. In fact, it is the only CH that we have here. And so now we get to this fragment. So far everything makes sense. Triplet bonded to 2 neighbors. We've got our 2. Quartet bonded to 3 neighbors, and we have 2, 3. So far so good. So let's look at the next one. We have this peak here, and this one becomes a little more difficult. We definitely have 1 peak in the center, 2, 3, 4, 5, 6, 7. We can clearly see 7 peaks, but it is possible there are 2 more, which leaves us the question, is this a septet, meaning 6 neighbors, or is it a nonet, meaning 8 neighbors? Could be either one. It could be that there are 2 more little peaks out at the edges that we can't see. It's definitely at least a septet, possibly nonet. So there are a couple of approaches. One, we can consider, what do we already have? So we have, for this hydrogen, we already have 2 neighbors. If it is a septet, it will have 6, meaning there should be 4 more. We don't have anything left that has 4 hydrogens. In fact, we have only 2 methyls. So this does not seem likely. So probably not a septet with 6 neighbors. What about nonet? Does this one make sense? Nonet is 8 neighbors, which would mean, since we already have 2, that we would have another 6. In fact, that matches very well with the fact that we have these 2 methyls out here. So that all seems to fit. Of course, we want to make sure that this part also matches. So we can look at that last peak. It is in fact a doublet, meaning that there is 1 neighboring hydrogen. Those methyl groups are bonded to a CH, which in fact fits. So it's bonded to a CH, which is why it's a doublet, bonded to a CH. And again, that indicates we have a nonet with 8 neighboring hydrogens. We've got 2, 3 more is 5, 3 more is 8. And so all of the splitting fits, and we have a final structure. Again, we always want to label our hydrogens, and so we would start labeling those. And again, notice that since we have 1 peak and both methyls are from the same peak, both methyl groups have the same label. Labeled 1E, the other is also labeled E. But other than that, we can simply start at one end and start lettering. So this is how you interpret an a nuclear magnetic resonance spectrum. Probably the best place to start is with the integration. Set the smallest value to 1 and determine what the others are. If you're getting a half, you'll probably want to double everything so that you have whole number ratios. And again, you may not get exact whole numbers, but they should be close so that you can evaluate that and round as necessary to get the values. That tells you whether you're dealing with a CH2 or a CH1 or a CH3 or possibly two CH3s. But it gives you that integration so you can determine that. Then use chemical shift. Identify your OH since you're dealing with an alcohol. Then look at chemical shift to identify your alkoxy, the OCH, and whether it's an OCH or an OCH2. And then use the splitting to determine what is bonded to what to get a final structure. And don't forget to label the hydrogens. And keep in mind when we are referring to the labels, those are to the hydrogens, not peaks. We do not refer to a peak. For example, we would not call this peak A. Peaks already have labels. That is the chemical shift. If you're going to refer to a peak, you refer to it, for example, as the triplet at 3.7 ppm. Or sometimes you'll see it written as delta 3.7. But that designates the fact that you're looking at a peak at 3.7. But we always use chemical shift when we refer to a peak. It's a peak at 3.7, or the peak at 1.7, or the peak at 1.4. We do not refer to peak A or peak 1. Always use chemical shift. So now that we know how to interpret a spectrum, let's move on to writing the lab report. Same guidelines as before: name, date, section number, title. Don't forget your unknown code and academic integrity statement. The abstract is going to be 2 or 3 sentence statements of what you were attempting to do, how you were attempting to do it, and a summary of your results. We express the objective not by saying the objective was to ... but rather by stating what we actually did. We don't include details here, but we do identify our results and also how we know those results. So let's consider this experiment. What was the objective? Well, the primary objective was to identify an unknown ester. How did we do this? Well, we did it from the constituent alcohol and carboxylic acid, which of course then means that we had to hydrolyze that ester so that we could then identify the alcohol and the acid. And so we have a few more objectives, and again, how did we do that? The hydrolysis was done with base catalysis. We identified the alcohol by NMR and the acid by the melting point. And we have to state the results. But again, we don't put this as the objective was, but rather we make a statement of what we were doing. So an example would be, an unknown ester was hydrolyzed using base catalysis to the corresponding alcohol and carboxylic acid. So we're telling what the objective was. An unknown ester was hydrolyzed. We're giving the objective by making a statement of what we actually did. Then, of course, we have to say how we did it. We did it using base catalysis. And then, what were the results? We got the corresponding alcohol and carboxylic acid. And we would do this with the other objectives as well. The alcohol was identified as 3-methylbutane-1-ol by NMR spectroscopy. Again, we are stating our objective by making a statement of what we did. The alcohol was identified. We state how we did it by nuclear magnetic resonance spectroscopy. And we give our results. It was identified as 3-methylbutane-1-ol. And you would do this for the other factors as well. How was the acid was identified as benzoic acid by melting point. And one of the results that you will be reporting, of course, is the percent yield. We do not report the mass yield, since that is kind of meaningless. Without knowing the scale we're running it on, we don't know if a 1 gram is a good yield or a poor yield, but we do report percent yield. We do not need to report how we determined that, since that should be intuitively obvious to a student at your level. For the chemical equation, you do need to write the equation for the specific ester that you had, and showing the specific structures of the acid and alcohol. Don't write a generic equation. Don't write something like ROOR prime. That would be generic. You have to draw out the specific ester that you used, ethyl benzoate or isopropyl toluate, whatever it was that you had. Write out the specific one, and likewise for the alcohol and the acid. And of course, you do have to use a chemical drawing package. You are not allowed to freehand draw anything like I did here. Procedure. Third-person passive voice. This is an account of what you did. Do not copy the procedure from the lab protocol. Those are written as instructions. It tells you, weigh out this, measure that. In this case, you're reporting what you did. You are not writing instructions. It should have sufficient detail for another student at your level to repeat what you actually did. So, for example, you could say the mixture was heated at reflux for 10 minutes. A student at your level should know what it means to heat at reflux. You do not need to mention the glassware at all. However, you do need to mention how long you refluxed. Reflux can be done for any indefinite length of time. It could be 10 minutes, it could be an hour, it could be a week. So you do need to specify how long you heated the reaction. Otherwise, a person could not repeat what you did. Likewise, a solution was washed with 15 milliliters of diethyl ether. A student at your level should understand what it means to wash a solution. They should know what glassware is involved, that you're using a separatory funnel, that washing involves mixing the liquids and venting and then separating the layers. All of that is implied when you say washed. You do not need to mention the glassware. You do not need to mention that the layers were separated. That is implied when you say washed. However, you do need to mention the solvent that you used and the quantity. Any number of solvents could be used to do a wash or an extraction. We use diethyl ether, but we could have used hexane or toluene, ethyl acetate, any number of other solvents, and also any different volumes. It could have been 10 mils, 15 mils, a liter. So you do need to specify the volume that you used. It is not necessary to state the obvious. For example, the 15 milliliters of diethyl ether. You do not need to mention that you measured 15 milliliters. That is obvious when you read the statement, the solution was washed with 15 milliliters. It is obvious at that point when you state the volume that you measured the volume. Likewise, if you report a mass of reagent that you used, it's not necessary to say you weighed it out. When you say you added 1.7 grams of sodium hydroxide to the solution, it is obvious that you weighed it when you give the mass. Final example, the white solid was recrystallized from 200 milliliters of boiling water. Again, a student at your level should know what it means to recrystallize. You do not need to describe the procedure that you used. You do, however, need to mention the solvent. Again, you could recrystallize from water. You could use ether as a recrystallization solvent, or ethanol. There are any number of different solvents. And the volume. The volume will be approximate. You generally don't measure out a specific volume. You won't have something like 210.7 mils. You can just simply say 50 mils or 100 mils, 200 mils, just approximate. And it's understood that for recrystallization, we rarely measure exact volumes. You do need to report the quantities and always show units. 100 milliliters is not necessarily the same thing as 100 grams. Report yield and percent yield. When you report the yield in mass, in grams, typically, you can just, right after that, put in parentheses percent. So you could have, for example, that you obtained 0.791 grams, and then in parentheses 52.1% of white solid, or if you know what it is, you could say 0.791 grams, 52.1% of benzoic acid. You do not need to put a separate statement that that percentage is the yield. It's understood when that follows the mass yield that the percentage is in fact the percent yield. Report melting point or boiling point when you measure those. Of course, that means you have melting point in this experiment. But also, right afterwards, in parentheses, give the literature value, and then a footnote or endnote to give the reference where you obtained that literature value. And as you did with the IR, you report spectral data at the end of the procedure. You have that spectral summary line. Identify the compound, then identify the technique. So for IR, you simply wrote IR. Here we write NMR. Then you give the medium and the units. The medium is for the NMR, for all of the alcohols that you have for this experiment, the NMR spectra were obtained in deuterochloroform. That D represents deuterium, the heavy isotope of hydrogen. But the symbol is just used as a D there. For IR, we reported a frequency of inverse centimeters. For NMR, we are not reporting an actual frequency. We use a proxy. Remember, we are measuring chemical shift, which is a proxy for the frequency. The chemical shift is denoted with this symbol, this Greek symbol delta. This is basically a lowercase d. If you type a lowercase d, you can then change it to symbol font or a Greek font, and you will get that delta symbol. And the units are ppm, or part per million. For IR, we simply reported the frequencies of the peaks. For NMR, we have more information, so we not only report our chemical shift, we also report the splitting, so T for a triplet, and the integration, so 2 hydrogens. The integration is not the number that's given underneath the peak. The integration that we report here is the normalized, the whole number value for the integration. So there might be a 0.7 under the peak, but if that corresponds to 1 hydrogen, you would put 1 H there. So this would indicate we have a peak at 3.7 ppm, that it's a triplet, and 2 hydrogens. Another peak at 1.7, the splitting as a non-net integration was 1 hydrogen. Common abbreviations, SDTQ for singlet, doublet, triplet, quartet. Anything greater than a quartet, you spell it out. So we don't put a P, we write pentet. Or for a sextet or septet, of course, we can't use an S since it already is reserved for singlet. We would write sextet or septet or octet, whatever we have. One other abbreviation, M, for multiplet. We use this if we don't know what the splitting is. This happens sometimes when you have peaks that are overlapping each other. It's hard to tell what the actual splitting of the individual peaks are, and so we simply put M for a multiplet. Calculations. Need to calculate limiting reactant, theoretical yield, and percent yield. Discussion. All spectral data need to be presented in tables. You did this for IR. You need to do it again for NMR. For the NMR, you're going to have 5 columns. The first is the chemical shift. The next one is the type of hydrogen. For the alcohols, it'll be one of 3 things. It's either going to be alkyl, which is just an ordinary CH, or it's the OH from the alcohol, or it is the alkoxy. So it's the hydrogen that's on the carbon attached to the oxygen of the alcohol. That's the alkoxy. Splitting, again, doublet, singlet, quartet, whatever, use the same abbreviations, spell out anything bigger than a quartet. And again, integration is the whole number values. And then the final column is the assignment. Remember, we label our structure, and then we make assignments, a specific hydrogen assigned to a specific peak. Of course, for this to make sense, you have to have the labeled structure. So you should have the structure with labels on it near the table, and of course the table should be near the discussion itself. The text of the discussion should be able to stand independent of the table. So if I delete the table from your report, I should still be able to read your discussion and understand what you are saying. If I have to refer back to the table, your discussion is incomplete. So tell me what is present in the spectrum. Then tell me what it means, and then draw conclusions. An example is given here. There's a peak at 3.7 ppm. The peak is a triplet, and it integrates to 2 hydrogens. So from that first sentence, I know what is present in the spectrum, or at least one of the peaks. Tell me what it means. This is in the alkoxy region, indicating the peak is for OCH2. The splitting indicates these methylenes have 2 neighboring hydrogens. Okay. So you're identifying the chemical shift and also telling me what the splitting means. Then make a conclusion. This peak corresponds to hydrogen B. So you should have a little snippet like this. Small number of sentences, can make them individual paragraphs if you want, for each row in your table. So I had 5 rows in my table because there were 5 different peaks. You should do this for each one of those. Likewise, melting point. Since you have multiple compounds, you should have a table with the unknown and all of the standard acids listed, along with their melting points. If you are simply comparing something you made with a single compound, it is not necessary to have a table. So for example, one of the experiments we do is the synthesis of tetraphenyl naphthalene. When you make it, you obtain a melting point. The only thing you're comparing it to is the melting point of tetraphenyl naphthalene, the known melting point. So in that case, you don't need a table. However, in this case, we have several possible acids that we could be comparing it to, and so all of the standards should be in that table, along with the melting point of your unknown. Again, discuss it, and the text should be able to stand independent of the table. That means you need to give the actual melting points in the text of your discussion. Don't make your reader refer back to the table. So example here, the unknown carboxylic acid had a melting point of 134 to 135 degrees Celsius. This compares with the melting points of 2-furan carboxylic acid and acetylsalicylic acid, indicating the unknown acid could be either of these carboxylic acids. You do not need to compare it to the other acids in the table to which it does not compare. If it only compares with one, you can just relate it to that one compound. However, if there are 2 possibilities, in this case 134 and 136 degrees are both plausible identities for this unknown, you would mention both of those. And then finally we have the summary. This is where you summarize the results, or you can also call this the conclusion. But basically here you will summarize your results, identify which alcohol you had, and how did you determine that. So for example, the alcohol was identified as 3-methylbutane-1-ol from the NMR spectrum. You don't need to go back into the interpretation again. It is sufficient to make that identification. But then you also need to do that with the carboxylic acid. And again with the ester, of course you also want to report the percent yield of the acid. Again, identify the carboxylic acid. Tell us how you made that determination. In this case, it would be from the melting point. You should report the percent yield of the acid. We don't have a yield for the alcohol since we did not isolate it. And you should have a comment on the acid, especially if it's over 100% yield, you should comment on why. If it's a low yield, you should probably also comment on possible reasons why it is low. And finally, which ester did you have? And from this, you would simply identify the ester from the parts. So if your acid in this case was furan carboxylic acid, so in this case, you would identify then the ester based on the alcohol portion, 3-methyl-butyl, and the the acid portion furan carboxylate. Of course, yours will be one of the esters listed in the lab protocols. The ones I've used in this example are not present. Going back to the abstract briefly, since the abstract does cover the conclusions, the results, you cannot write your abstract until after you've done your analysis. Once you've done your analysis, you should be able to go and write your abstract. So oftentimes it's convenient to write the rest of the report first and then go back and write your abstract. So even though it's at the beginning of the report, it's often convenient to write it after you've written the rest of the report, since you have to do all of that analysis beforehand anyway. The NMR can sometimes be a little difficult to interpret. Since there is so much information, it is more complex than interpreting an infrared spectrum, but at the same time it gives a lot more information. So it's a good idea not to wait until the last minute to try to write your report, so that if you do have any questions or difficulties, you have time to ask your instructor for assistance and give your instructor time to get back to you. So don't put this off. Start it early.